Alright, so in this video I'm gonna be explaining another important article with the title Domain2Vec, Domain Embedding for Unsupervised Domain Adaptation. So we are mapping a domains to vec, just like we map word to vec. For any word we have a vector. Now this idea is that for any domain we can have a vector. And in my understanding you can always generalize even this article by saying that you have infinite number of domains. Just like we can do word2vec, it's an high dimensional space. So you can generalize it, so you can see domains as a continuous variable instead of just discrete variable. Instead of saying domain from 1 to 10, you can say domain from 1 to, for example, infinity or 1000. So this paper in 2020 is very important. It is written by Stanford and Boston and IBM, MIT. Conventional unsupervised domain adaptation studies the knowledge transfer between a limited number of domains. This neglects the more practical scenario where data are distributed in numerous different domains in the real world. A technique to measure domain similarity is critical for domain adaptation performance. Just we have in word2vec, we have a technique to see the difference between the two vectors. Same way we want to measure the domain similarity. What is the difference between domain I and domain J? How similar they are. To describe and learn relation between the different domains, we propose a novel Domain2Vec to provide vectorial representations of visual domains based on joint learning of feature disentanglement and gram matrix. To evaluate the effectiveness of our Domain2Vec model, we create two large-scale cross-domain benchmarks. The first one is tiny domain adaptation, which contains 54 domains and about 1 million MNIST style images. The second benchmark is domain bank, which is collected from 56 existing vision datasets. So you see the architecture by joint learning of feature disentanglement and gram matrix. So this is the disentangler, that we have domain specific and category specific. We always have a domain classifier to distinguish domains. And as usual, for this task, they have classifier to have different classes as well. But interesting thing about this paper, they have a reconstructor as well. And we will go through each of them. And this is the gram matrix that provides deep domain embedding. Because as I said, instead of word2vec, now we are doing Domain2Vec. So for each domain, we have an embedding here, which is provided by this gram matrix. And you have 56, for example, domains. 56 datasets are computer vision. Or even in NLP, for example, you have different corpora, different, for example, Twitter text, or weblog, or news, different kinds of text, different domains. In this paper, we introduced Domain2Vec to represent domains as element of a vector space. Formally, given n distinct domains, the aim is to learn a domain to vector mapping. We would like our Domain2Vec to hold the following properties. Given two domains, d sub I and d sub j, the accuracy of a model trained on d sub I hat and tested on d sub j hat should be negatively correlated to the domain distance in a vector space V. For example, smaller domain distance leads to better cross-domain performance. For example, pictures of cat with dark blue is close to pictures of cat with background of blue, for example, or black. So our domain embedding can be used to reason about the space of domains and solve many unsupervised domain adaptation problems. As a motivating example, we studied the problem of selecting the best combination of source domains when a novel target domain emerges. So the good thing about this, if you map it to a vector space, then a combination of your source domains, it's a new novel target domain. An unknown, it could also be used for domain generalization because there we don't have access to target domain. Computation of Domain2Vec leverages a complementary term between the gram matrix of deep representations and the disentangled domain-specific feature. Gram matrices are commonly used to build style representations that compute the correlations between different filter activations in a deep network. Since activations of a deep network trained on a visual domain are a rich representation of the domain itself, we use gram matrix to capture the texture information of a domain and further obtain a stationary multi-scale representation of the input domain. Specifically, given a domain defined by d hat with n sub I examples, we feed the data through a pre-trained reference convolutional neural network, which we call feature generator. Some articles say backbone, some articles say it's just a generator. For example, in adversarial setting, we fool the discriminator by designing a good feature generator. So let's carry on. So we compute the activation of the fully connected layer as the latent representation of f sub g. Inspired by a feature disentanglement idea, we introduce a disentangler D to disentangle f sub g into domain-specific feature and category-specific feature. Finally, we compute the gram matrix of activations of hidden convolutional layers. Given a domain, we average domain-specific features of all the training examples as a prototype of domain D hat. So let's carry on. Where we define our domains D1, 2, and then define a domain, and we want to learn a domain to vector mapping. This phi is very important. We want to map from domain to a vector space, which is capable of predicting domain similarities. So first feature disentanglement. Given an image labeled pair X and Y, a deep neural network is a family of function probability of Y given your X, Y is the label of your image X, trained to approximate the posterior by minimizing the cross-entropy loss, where P hat is the empirical distribution defined by the I's domain, where with n sub I training examples. So the latent representation are highly entangled with multiple hidden factors. We propose to disentangle the hidden representations to domain-specific and category-specific features. Figure 1 shows the proposed model. Given n domains, the feature extractor G maps the input data to a latent feature vector which contains both the domain-specific and category-specific features. The disentangler is trained to disentangle the feature to domain-specific feature and category-specific feature with cross-entropy loss and adversarial training loss. The feature reconstructor is responsible to recover that latent representation from pair, aiming to keep information integrity in the disentanglement process. So we have category disentanglement. Given an input image, the feature generator computes the latent representation f sub g, and our category disentanglement is achieved by two-step adversarial training. First, we train the disentangler D and the keyword category classifier C to correctly predict the class labels, supervised by the cross-entropy loss. In the second step, this step is very important. We aim to remove the domain-specific information from F. Assume that we already have a well-trained domain classifier. We freeze the parameters in domain classifier and train this. Of course, I've seen a paper that they don't remove the domain-specific. They embrace it. They use it for domain generalization, of course. But this paper is about domain adaptation. This adversarial training process corresponds to blue dotted line in figure 1. And then we have domain disentanglement. To achieve, so we first train the feature generator, G, and disentanglement D. So D of G is your F. So F is your D of G, discriminator, disentangler of generator. So in the second step, we aim to remove the category-specific information. Okay, remove it. Assume the classifier has been well trained. We freeze the parameters in the category classifier and train this disentangler to generate F, aiming to fool the category classifier. This adversarial training process corresponds to red in figure 1. And then we done feature reconstruction. We do reconstruction and also minimizing the KL divergence between Q and P. So the first term just wants to recover the original features extracted by G, but the second term calculates the Kullback-Leibler divergence, which penalizes deviation of latent feature from prior. So we have a prior. We don't want that to move from that prior too much. So we keep it by just this KL loss. And then mutual information minimization, and then deep domain. Now that we can do deep domain embedding, the feature correlations are given by the Gram matrix, where G is the inner product between the vectorized feature map between I and J. And then they eliminate sparsity, the domain-specific feature, and Gram matrix as are high sparsity data. And then, so we have different kinds of losses: class, specific domain, reconstruction, and this mutual information. And that's it.